Good afternoon, ladies and gentlemen. I would like to present you our paper about the characterization of the fatigue behavior of selective laser-sintered thermoplastic materials. We investigated both polyamide 12 and also thermoplastic polyurethane materials in this study. After a short introduction, then I would deal with our test, with the experiments, with materials, with specimens and test parameters. Then shortly discuss all results, both the monotonic test and also cyclic test, dynamic characterization and fatigue, and then a short summary and conclusion of the results. We are dealing with different materials and with different processing methods. And in addition to the conventional processing, additive manufacturing became important, both as an individual process technology, but also as an extension to other processing methods like composite processing. In order to improve this, we also implemented at the Institute a robot-assisted additive manufacturing system. And with this system, we are able to functionalize different unreinforced or fiber-reinforced structures. And these reinforced can be designed with a high freedom. Does it mean we can realize honeycomb-like structure like here, but also different other structures? And recently, for example, lattice-like structures became important and are investigated very intensively by different researchers. We have also a research project, Multiscale Optimization for Additive Manufacturing for fatigue-resistant and shock-absorbing metamaterials. And in this project, we are dealing with different structures. In the photos, you see quadratic structures, bistable structures with lattices, with linear and non-linear lattices. In the right side, a cylindrical configuration of these structures, and then also the left side at the bottom, specimen configuration, because we would like to also test this auxetic or normal lattice or bistable lattice structures. And in addition to the stiffness, the strength and especially the durability, the fatigue behavior plays an important role. And the laser sintering, the parameters, influences significantly the behavior, especially the fatigue behavior of these materials. Imperfections plays an essential role also in this process. The other aspect is the application. We would like to apply these lattice-like structures for components which are exposed to cyclic loading. Here, schematically, the several selected aspects of the human locomotion. One case study is dealing with a novel shoe sole system, either using these quadratic lattice structures integrated in a novel shoe sole, or using the cylindrical structures and form pimples in another structure. Two key parameters, two key properties plays a role. First of all, the elasticity or the inherent viscoelasticity of these materials. Shock absorbance depends on the viscoelastic behavior, and the damping is essential for this application. However, we are targeting also long-term behavior, hence the fatigue became important. Does it mean we would like to characterize the materials then both for performance and also for durability? Here in this slide, I show the different techniques which can be used for the fatigue characterization of elastomers. On one hand, you can use the conventional methods based on Wöhler curves. However, in contrary to stiff materials, also stiff polymers, you can not only use force-based cyclic test, but also you can use a kind of displacement-based analysis. Does it mean the control parameter during the cyclic loading is not the force or the force amplitude, rather a displacement amplitude? We are using typically dumbbell cylindrical specimens, like a dumbbell, or this diabolo shaped specimen for this fatigue characterization. Does it mean both the critical stress and also the critical strain can be used for characterizing the fatigue behavior? An additional fracture mechanics based on the fatigue crack growth curve, the crack growth rate, and the tearing energy. And the tearing energy is calculated based on the hysteresis curves of the materials investigated. In this study, we used the force-based cyclic test first, and in the recent study, we continue with the displacement or strain-based analysis. The objective of our study was to characterize the deformation of the failure behavior of laser-sintered polymeric materials under various process conditions and under various test conditions. And also we would like to determine model parameters for simulation models, both for reversible deformations and also for irreversible deformations. Then the experiments, we use different parameters. First, the material grades, as I mentioned, polyamide 12 and thermoplastic polyurethane. We use different cylindrical specimen geometries. Also, we applied different printing orientation or printing direction. Does it mean we used the specimens perpendicular and parallel to the printing direction? And also, we change then surface properties and testing rate, and for the cyclic test, the stress ratio. And also the specimen geometry with and without notch. Does it mean there is a hollow cylindrical specimen and a smooth notched specimen which used for this fatigue test? I would like to emphasize that in addition to the axial loading, these cylindrical specimens can be tested also under torsional loading conditions, and the axial and the torsional loading can be combined. Does it mean we can realize a wide range of complexity multi-Excel loading? Recently, we performed the tensile and compressive loading, both under monotonic and also cyclic loading conditions. And then we will continue later with the torsional characterization. The first results of the monotonic tensile test in a very classical way, load displacement curves for polyamide 12 and also for TPU material with the different orientation, transverse and parallel, and notched and hollow cylindrical specimens. And as we expected, we see the differences between notched and unnotched, and of course we see significant difference between the printing orientation, transverse and parallel. Also, of course, we can see the difference between polyamide and TPU. The thermoplastic polyurethane materials are softer, reveal lower modulus values, But as you see, there is significantly higher fracture strain values. Hence, and because this is also my favorite material, we deal then with this material in this presentation. Here you see the results of the monotonic tensile test and the comparison of the notched specimens with the hollow cylinder, does it mean the unnotched specimens, for both printing orientation. You see the difference, and if we compare stiffness at low strains, the strength, the maximum load, or the fracture strain, then we see that the highest difference between parallel and transverse we can recognize in the fracture strain. Does it mean the specimens where the where the printing orientation was in the loading revealed significantly higher fracture strain values for both materials. In these monotonic curves can be used for a phenomenological modeling. Does it mean we can determine modulus values? We determined also Poisson's ratio values. We determined tensile strength values, and these curves can be used for elastic plastic material models. And hence, we used rate-dependent, we performed rate-dependent tests from 0.1 to 100 millimeters per second. We were able to determine material model parameters for elastic viscoplastic material models. And from the monotonic test, we moved to the more interesting cyclic test. And as I mentioned, I would like to characterize the deformation behavior, and due to the inherent viscoelasticity, we need the viscoelastic parameters. First, conventionally, we performed dynamic mechanical analysis test and determined the E prime, does it mean the storage modulus and also the loss modulus, and then tangents delta values for both materials. Here I am showing the thermoplastic polyurethane for both printing orientation, the 90 and the 0. And then we can see the classical trends typical for thermoplastic polyurethanes. Interestingly, above 80 degrees C, you can observe a softening. Does it mean the difference between the orientation is vanishing at high temperatures? Furthermore, we also performed this test frequency dependent in a frequency range from 0.01 to approximately 50 Hertz at different temperatures in order to construct master curves. And then you see here the master curves for the thermoplastic polyurethane material and also for both orientation. Does it mean we have a kind of anisotropic master curves or anisotropic viscoelasticity models based on this test? On the left side, you see the storage modulus values, but we also determined loss modulus and then calculated tangents delta, and not only constructed a master curve for the modulus, but also constructed a master curve for the damping behavior. If you fit, for example, these curves, these master curves, using the generalized Maxwell model, you may determine the parameters of a Pruni series, which is the most typical linear viscoelastic model for viscoelastic deformation analysis. This is also available. Does it mean we have characterized the orientation dependent, anisotropic, small strain deformation behavior, viscoelasticity for these materials. Then finally, using the same specimen and same test setup, we perform fatigue test, very similar to the conventional fatigue test, at two stress ratios, -1 and 0,1. And also for both printing orientation, does it mean the parallel and the perpendicular? And you see these results for both the notched specimens and also for the hollow cylindrical unnotched specimens at 5 Hertz. And as you see, there is a clear ranking between the materials. The specimens parallel with with the stress ratio 0.1 revealed the highest stress values. Then the other specimens perpendicular or 90 degree and -1 revealed the lowest fatigue resistance. You can fit then the curves if you want with conventional methods. You can use Baskin or any other model. At the moment, we are focusing on the experimental determination or estimation of the durability limit value in the range of up to 5 million cycles in order to give information then for long-term behavior. Then, in a short discussion, we can clearly state that the printing orientation is clearly visible in the stress-strain curve. The stiffness and the strength is influenced, but the most important difference observed in the fracture strain values. The influence of the smooth notch in the specimen geometry is visible, but it seems to be overshadowed by the printing orientation and the anisotropy effect. The monotonic and the cyclic test revealed very similar tendencies. We try to compare with injection molded specimens and injection molded materials with previous results. It's hard to really compare, but roughly we can state that in printing direction we have a difference about 20%, and perpendicular to the printing direction we have significantly lower values in the SLS printed materials. And then finally the acknowledgement of the project, and also my acknowledgement. Thank you very much for your kind attention. Thank you.